Welcome back to our study of the fundamentals of operating systems based upon the textbook Operating System Concepts, 10th edition by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. In the last lesson, we discussed process creation, parent-child relationships between processes, and so on, and then we began to investigate process communication. We found, for example, that there are two general forms of communication between processes, one being a message passing technique and the other using shared memory, common memory shared by the two processes. We also remember that one of the jobs of the memory manager is to protect the memory of one process from another process. So this process of shared memory tends to override that responsibility to a degree, and the two processes become responsible for protecting the shared space. In this lecture, we're going to begin our discussion of message passing, another technique for inter-process communication. We'll pick up where we left off from the last lesson. In fact, I'll play a little bit of the last lesson just to make sure that our conversation flows. The producers and consumers scheme requires that these processes share a region of memory and that the code for accessing and manipulating the shared memory can be written explicitly by the application programmer. Another way to achieve the same effect is for the operating system to provide the means for cooperating processes to communicate with each other via a message passing facility. Message passing provides a mechanism to allow processes to communicate and to synchronize their actions without sharing the same address space. It's particularly useful in a distributed environment where communicating processes must reside on different computers connected by the network. For example, an internet chat program could be designed so that the chat participants communicate with one another by exchanging messages. A message passing facility provides at least two operations: send message and receive message. Messages sent by a process can be either fixed or variable in size. If only fixed size messages can be sent, the system level implementation is straightforward. This restriction, however, makes the task of programming more difficult. On the other hand, variable size messages require more complex system level implementation, but the programming task becomes easier. This is a common kind of trade-off seen throughout the operating system design. If processes P and Q want to communicate, they must send their messages to and receive messages from each other. A communication link must exist between them. The link can be implemented in a variety of ways. In our case, we're not concerned with the link's physical implementation, but we are concerned with its logical implementation. Here are several methods for logically implementing a link and the send-receive operations. First, there's direct or indirect communication. Then there's synchronous or asynchronous communication. And finally, there's automatic and explicit communication. Processes that want to communicate must have a way to refer to each other. They can use either direct or indirect communication. Under direct communication, each process that wants to communicate must explicitly name the recipient or sender of the communication. In this scheme, the send-receive primitives are defined as shown here. Send open paren P and the comma the message, which means you have the send command with two arguments. The first one, P, indicates the destination, and after the comma, the second argument is the message. Then receive, open paren Q, comma, message, close paren, is indicating that we're receiving a message from process Q, and then after the comma, what the message is. A communication link in this scheme has the following properties. A link is established automatically between every pair of processes that want to communicate. The processes need to know only each other's identity. A link is associated with exactly two processes. Between each pair of processes, there exists exactly one link. This scheme exhibits symmetry in addressing. That is, both the sender process and the receiver process must name the other to communicate. A variant of this scheme employs asymmetry in addressing. Here, only the sender names the recipient. The recipient's not required to name the sender. In this scheme, the send and receive primitives are defined as follows. Send open paren P, comma, message, which sends the message to process P, and then receive open paren ID, comma, message, which receives the message from any process. The variable ID is set to the name of the process with which the communication has taken place. The disadvantages of both schemes, symmetric and asymmetric, is the limited modularity of the resulting process definitions. Change in the identifier of a process may require examining all other process definitions. All references to the old identifier must be found so that they can be modified to the new identifier. In general, any such hard coding techniques where identifiers must be explicitly stated are less desirable than the techniques involving indirection, as we'll talk about next. With indirect communication, the messages are sent to and received from mailboxes or ports. A mailbox can be viewed abstractly as an object into which messages can be placed by processes and from which messages can be removed. Each mailbox has a unique identifier. A process can communicate with another process via a number of different mailboxes, but two processes can communicate only if they have a shared mailbox. The send and receive primitives are defined as follows. Send open paren A, comma, message sends a message to mailbox A. Receive open paren A, comma, message receives a message from mailbox A. In this scheme, a communication link has the following properties. A link is established between a pair of processes only if both members of the pair have a shared mailbox. A link may be associated with more than two processes. Between each pair of communicating processes, though, a number of different links may exist, with each link corresponding to one mailbox. Now suppose that processes P1, P2, and P3 all share mailbox A. Process P1 sends a message to the mailbox A, while both P2 and P3 execute a receive from A. Which process will receive the message sent by P1? The answer depends on which of the following methods we choose. 1, we could allow a link to be associated with two processes at most. 2, we could allow at most one process at a time to execute a receive operation. And 3, we could allow the system to select arbitrarily which process will receive the message, that is either P1 or P2, but not both. The message may define an algorithm for selecting which process will receive the message. Round robin, where processes take turns receiving messages, is one example. The system may identify the receiver to the sender. A mailbox may be owned either by a process or by the operating system. If the mailbox is owned by the process, this means that the mailbox is part of the address space of the process. In this case, we distinguish between the owner, which can receive messages through this mailbox, and the user, which can only send messages to the mailbox. Since each mailbox has a unique owner, there can be no confusion about which process should receive a message sent to this mailbox. When a process that owns a mailbox terminates, the mailbox disappears. Any process that subsequently sends a message to the mailbox must be notified that the mailbox no longer exists. In contrast, a mailbox that is owned by the operating system has an existence of its own. It's independent and not attached to any processes. The operating system must then provide a mechanism that allows a process to do the following: create a new mailbox, send and receive messages through this mailbox, and delete a mailbox. The process that creates a new mailbox is that mailbox's owner by default. Initially, the owner is the only process that can receive messages through this mailbox. However, the ownership and the receiving privilege may be passed to other processes through appropriate system calls. Of course, the provision could result in multiple receivers for each mailbox. As we have seen, communication between processes takes place through calls to send and receive primitives. There are different design options for implementing each primitive. Message passing may be either blocking or non-blocking, more often referred to as synchronous and asynchronous. As you can see here, with blocking send or synchronous, the sending process is blocked until message is received by the receiving process or by the mailbox. On the other hand, using asynchronous communication or non-blocking send, the sending process sends a message and resumes operation. Using block and receive, the receiver blocks until a message is available, while with non-block and receive, the receiver retrieves either a valid message or a null. Different combinations of send and receive are possible. When both send and receive are blocking, we have a conversation between the sender and the receiver. The solution to the producer-consumer problem of managing shared memory space becomes trivial when we use blocking send and receive statements. The producer merely invokes the blocking send call and waits until the message is delivered to either the receiver or the mailbox. Likewise, when the consumer invokes receive, it blocks until a message is available. When communication is direct or indirect, messages exchanged by communicating processes reside in a temporary queue. Basically, such queues can be implemented in three ways. Zero capacity. The queue has a maximum length of 0. Therefore, the link cannot have any messages waiting in it. In this case, the sender must block until the recipient receives the message. Or it could be bounded capacity. The queue has a finite length, n, let's say. Thus, at most, n messages can reside in it. If the queue is not full when a new message is sent, the message is placed in the queue. Either the message is copied or a pointer to the message is kept. And the sender can continue executing without waiting. The link's capacity is finite, however. If the link is full, the sender must block until space is available in the queue. And finally, there's unbounded capacity. The queue's length is potentially infinite. Thus, any number of messages can wait in it. The sender never blocks. The zero capacity case is sometimes referred to as a message system with no buffering. The other cases are referred to as systems with automatic buffering. So there you have the end of Unit 1 of Module 2 on the memory management system. This unit was on processes. And go back and study your notes, and when you're ready, come on back.